I'll begin with a word of prayer. Heavenly Father, we thank you for this day again, Lord. Thank you for these students. Just ask you bless this class today. Help us to glorify you in what we do, Lord. In your name I pray. Amen. So yes, I brought a visitor. This is my son, Matthew. How old are you? 4. Right. And I also brought a handout. Now, okay, so I asked the registrar to add Nathaniel by email last Friday, and he's still not added. So I'm not sure what the deal is. I gather the registrar has a backlog of emails. So if you want to not wait and have me fill out the form, I'll fill it. You can go over and do it in person. I don't know what's the problem. Usually they do it within a day, so it's faster to just send the email, but I may be wrong this semester. So if you're just tired of waiting and you want access to Blackboard and all that good stuff, just bring me the form, I'll sign it. I try not to because I'm trying to save you guys time, but my bad. So sorry about that. So because not all of you have access to Blackboard, I thought it would be wise to just give you a copy of Mission 1. So you take one of these, and if you already have a copy that you are in Blackboard, and you already have a copy, if you'd not take it, that'd be great. Because I made 35. How many people are in here? May not even be an issue. We got what? 3, 8, 11, 16, 21, 25, 29, 32. Oh, I think you can. Everybody can take one if you want. Actually, I think I had enough. And then this is a handout. What I did was I copied the review problems from a textbook called Rogakowski, and so what I have is like at the end of the chapter they have the review problems in a lot of books. So I have those as well as the answers from the back of the book. I just made a little handout for you guys, and so I'll recommend some of these towards those daily quizzes I was talking about, because the problems I was showing you that I have solutions written for, right, in the back of the text, in the back of my chapters. Well, those are fine, but we'd like a few more problems to kind of bounce off of. So I think that will help fill the gap. So I'll talk more about those a little bit later. So maybe tomorrow we'll have our first daily quiz, if I can sort out the roster. I guess if you're not on the roster yet, you're safe, but the rest of you I can start quizzing. Yes? No? Okay. Oh, yes, attendance. So if you're here, check the box, the second box, right? And if you're not, well, don't. Thank you. Any questions about anything? Yeah. So the daily quiz, it could be on anything we've covered up to the day before, and the problems I recommend from the recommended homework, none of which I've recommended yet. So at the moment, pretty much just examples in class, of which there have been precious few up to this point. All right? So let's remedy that. Now, not everybody takes the daily quiz. What's going to happen is I'm going to write all your names on a 3x5 card, and then I'll pick out at random 3 or 4 probably, and then have you come up on the boards and write out the problems. We'll take the first few minutes of class to do that. I will not videotape you. All right? And then, once that's settled, I'll turn the camera on and we'll dissect the results. All right? So something like that. Of course, I haven't worked out all the kinks yet, but I think that will help keep you guys up to date with the course and help discourage you from trying to cram for the test, which is, for some reason, very popular and almost a badge of honor, right, amongst engineers especially. But it's a really, really bad way to learn math. Yes?
Are we doing the same thing for the missions as last semester? Do you want us to only use one side of the notebook paper?
Yes, your solutions for the missions should be one-sided. Yeah. Yep. I think I say that. Let me see here. Copying answers and steps is strictly forbidden. Evidence of copying, results, blah, blah, who cares about that? Working together is encouraged. Share ideas, not calculations. Explain your step. This sheet must be printed and attached to the assignment as a cover sheet. The calculation and answers should be written neatly on one side of paper, which is attached and neatly stapled in the upper left corner. Box your answers where appropriate. Please do not fold. So it's all right there. Yeah. The one exception to that, of course, is the cover sheet, which I just made two-sided. Sorry about that. I won't take points off for that. That would be really ridiculous. But but kind of funny. Just the rank unfairness of doing that. All right, enough about that. Any other questions about procedural stuff? Oh yes, thank you. Okay, so let's keep talking about vectors and points and all that. So last time I pointed out that there's a correspondence, an obvious correspondence between vectors, directed line segments from the origin, and points, right? And the correspondence is pretty simple, right? If I look at this point out here, point P, and I look at this directed line segment like that, well, P is equal to P vector, right? Where here, I'm suggesting P is P1, P2, P3, whereas P vector, again, is a directed line segment. Now, to be less ambiguous, maybe we shouldn't say just directed line segment. Maybe we should say where the directed line segment's attached, right? So if we were to say that, this is basically shorthand for P1, P2, P3 at the point 0, 0, 0. Oh no! Don't worry, it's okay. Some of the crayons did not survive, but you know, so you could write like a little sub. Hey, what point the vector's at if you wanted, right? You could attach a base point, but traditionally we don't do that. We just write this vector, and then we use language to describe where the vector is. All right. But of course, you could work in a more clunky notation where you had the direction of the direction of the vector and the point at which it was attached. But nobody does that at this course. All right, so let's talk about this. Here's x, here's y, here's z. And if I was to take 2 points, right, say a point P and a point Q, right, I could also find the vector which connects those 2 points, right? If I want the vector which is based at P and points to Q, right, the usual notation for that, here let me draw a picture of it, base point P, terminal point Q, this vector, we typically say PQ vector, all right? That's the vector which goes from P to Q. Now, the formula for that, in terms of like algebra, well, this is actually Q minus P. Now, let me just draw a separate. Thank you. Got some Wookiees, C-3PO. You guys seen the bad lip reading Star Wars? Yeah, my brother started me on that about a week ago. I love the C-3PO with the Indian voice. I want more of that. There's just like about 20 seconds of it, but I want more of that. Anyway, I digress. Thanks, Matt. All right, so to understand this, it's maybe helpful to just draw another picture. If this point is P and this point is Q, right? Then if we look at this vector, P to Q, like that, right? Well, let's see here. Where is Q, the Q vector? From the origin, this is Q, right? And how about P? P is this vector, right? Which we identify with that point, right? So can you see what should be true here? Remember the tip-to-tail vector addition? How's it work? We've got Q, right, plus PQ. What should that be equal to? See that? This vector plus that vector. Oops, I'm an idiot. I can't follow the arrows. What should I have done? I should do P, right? Sorry, vector P plus vector PQ gives me what? that resultant is q, right? So p plus pq should be equal to the q vector based at the origin. Do you see that? So that's why we have, if we solve this, this gives us that pq is equal to q minus p. And of course, you could put vectors over this if you like, but when we're talking about vectors based at the origin, we can just drop the vectors and just write the points if we want. So this right here is an important idea. To find the direction vector from one point to another, we take the difference of their coordinates, their coordinate vectors, p and q. All right, enough about that. So let's talk about components. So if you look at a vector here, let's say vector A, B, C, all right? We can break that into pieces, right? We can say that's actually this piece right here. Let me just drop this down. So that's the projection of that point, this point here, all right? Which again corresponds to this vector based at the origin. Let's give it a name. Let's call it vector v. All right. So that vector v can be broken up into three pieces. We have, yes? You what? Okay, sorry about that. So if we go back to here, we've got this piece, right? So we could say it's this vector, right? This vector along the x direction. And then we have this vector along the y direction, right? And then a third vertical vector. We can break up the vector v into three pieces. We can break it into an x piece, a y piece, and a z piece, right? This is not surprising, right? This is basically like in 2 dimensions, you know this is Etch-a-Sketch, right? Like to get for any point on the Etch-a-Sketch board, you have to go that many horizontal, that many vertical, but you can't go anything else, right? But somehow, just by doing horizontal and vertical, you can get anywhere. In the same way, we can build vectors in 3 dimensions from a sum of an x piece, a y piece, and a z piece, as you can see. What are those specifically, though, in terms of that notation? This is what? This is A, 0, 0. The red one is what? 0b, 0. The blue one is 0, 0c, right? So if you look at that, we can actually write this as the sum of 3 things. In particular, A, 0, 0 plus 0b, 0 plus 0, 0c. Okay. Now, how do we define scalar multiplication last time, right? So we can pull the a out. This is a times 1, 0, 0, plus b times 0, 1, 0, plus c times 0, 0, 1. I'm deliberately going back and forth between 2 ideas. There's 2 major themes to what I'm doing right now. The one theme is geometry, right? The other theme is algebra. And the beauty of this vector analysis is that it marries these 2 ideas. It gives us a way of doing geometry with algebra. You see, this picture is equivalent to that calculation, right? Some of you are more gifted geometrically, some of you are more gifted algebraically, but we have options in here, right? You can go one way or the other. Now, this is a lot to write. So we have a special notation for these. This is what I call x hat. This is what I call y hat. And this right here is what I call z hat. Right? So in other words, you can summarize what I just said as saying the vector v can be written as ax hat plus by hat plus cz hat. Excuse me. Now, if you look in most calculus books, This is not the notation which is used. This notation I learned in physics. I was a double major in math and physics. It's where a lot of my ideas come from. This is my background in physics. And the reason I prefer this notation is it generalizes. But in many engineering books and other calculus books, you'll see the notation I, J, and K. But in the textbook, they're bold. Most of you don't carry around bold pens, right? So students have to put hats on these as to not be ambiguous. That says they're unit vectors. When you put a hat on something, it becomes what's called a unit vector. I'll explain that more as we go on today. This, bless you, this IJK notation is ancient. Well, I don't know how ancient it is. It's kind of old. It goes back to before the Civil War, like 1843 something. These are Hamilton's quaternions. Well, these are not Hamilton's quaternions. Actually, these are vectors, which replaced Hamilton's quaternions. But we still use IJK in honor of Hamilton, except that I don't, because I don't care about him. So because I prefer a more logical notation, x hat, y hat, z hat, right? I mean, what is x hat? It's a vector of length 1 that points in the direction of increasing x. Y hat, what is it? It's a vector of length 1 that points in the direction of increasing y. What's z hat? It's a vector of length 1 that points in the direction of increasing z. Guess what r hat would be for us later? And what would theta hat be? R hat would be a vector of length 1 which points in the direction of increasing r. Theta hat would be a vector of length 1 that points in the direction of theta, increasing. Where r and theta are polar coordinates, which you saw last semester. So my notation is universal. It's not this weird IJK notation, yeah.
So A, B, and C are meant to be scalar.
Yeah, yes, A, B, and C, these are, that's a very strange, anyway, these are numbers, yeah, real numbers. Right. Okay, so language. Ax hat is the x vector component of V. All right? On the other hand, A is the just the x component. Or if you want, you could say it's the scalar, the x. I mean, by default, if we say component, we're saying scalar component. So if I want the vector component, I'll say as much. What's the difference between A and Ax hat? It's a significant difference. A is a number. Ax hat is a vector. It's a directed line segment. These are different things. Okay. Any questions? Right. I will eventually get to examples, but I need to build a little bit more before we can do that. Yeah.
So why do you draw the graph thing with x coming towards us? Wouldn't it be more familiar if c was coming towards us?
I don't know. You could, you have choices, of course. You could do that. If you wanted to make z coming towards you, that would, let's see here. Let's see here. Yeah, mostly it's because I want to picture the xy plane as horizontal for a lot of things. And let me think about that. If I want that to be, if z is coming out of the board, I need x cross y being z, whatever cross is. Some of you know. X cross y would be z. So that would force us to draw a picture like this. Do you like that? That's why z doesn't go out of the board. Because if we use the right-handed coordinate system, that's the axes we'd have to choose. Yeah. So anyway, yeah, this is pretty much the standard picture. Other questions? I mean, I am happy to have questions. All right, so now we know how to find vectors between points, right? We just find the coordinates of the point and find the vector that connects them. For example, find vector between, how about this, vector with terminal point 1, 2, 3, and base point 0, 7, 13. Okay, so what would that vector be? So we do, I'll call this thing P. I'll call this thing Q for the sake of labeling. So if I have base point Q and I have terminal point P, what am I looking for? I'm looking for vector what? PQ or QP? Right, I'm going from Q to P. And the formula for that is P minus Q, right? By our discussion over here. And so in particular, this is 1, 2, 3 minus 0, 7, 13, which is equal to 1 minus 5 minus 10. All right? That's kind of about the most exciting example I can think of at the moment. Let's continue to develop some more material, okay? I guess I could ask you, what's the z vector component of this vector? How about this? Minus 10 z hat as its z vector component. Does that make sense? Yeah.
We actually, is that accepted notation though, writing that a point subtracted from another point is equal to a factor?
Yes.
Really? Okay.
This notation is based on the discussion we've had up to this point, identifying, points at the origin, vectors based at the origin with those points. And, you could just as well, I'm going to write vectors when I'm emphasizing it's a vector. If you want to get picky, you could put parentheses there, but the reason I write angle brackets there is to emphasize that it's a vector, conceptually. Okay, so how about distance between points? So I usually just think about the distance from the origin to a point, let's say ABC, right? Actually, let me say the point is what? How about x, y, z? That's kind of, why not? So what's the distance from the origin to that point? So again, I think it's helpful perhaps to look at the projection of the point down into the xy plane, which is xy 0, right? And so with that in mind, I can ask you what's the length of this vertical dotted line? Yeah, assume we're x, y, and z are positive. If we can derive this, it's pretty easy to see that if x and y and z have different signs, the same formula will hold. But so yeah, the distance, the length would just be z. And then, all right, so if you look at this line in the xy plane from the origin, this blue dotted line, you can see a right triangle in the xy plane, right? And in particular, you can look at this right triangle right here, right? Put a little right triangle symbol in there. So that's a right triangle. The blue dotted line is its hypotenuse, right? What are the lengths of the adjacent and, what are the lengths of the non-hypotenuse sides here? Yeah, x here and y here. So what's the length of the blue dotted line? Right. And then if you use your imagination, you can see that there's a vertical plane, right? A plane which is perpendicular to the xy plane, and that plane also contains the z-axis in it, right? And in that plane that contains the xy, that's perpendicular to the xy plane and contains the z-axis, there's another triangle, right triangle, this one, right? Here's the right angle. And so by the Pythagorean theorem, in 2 dimensions, if you like, you can apply that to this green triangle. And what does that tell us about this distance here? D is equal to the square root of what? X squared plus y squared squared plus z squared, right? And so what's the formula then? the distance from the origin out to the point x, y, z is the square root of x squared plus y squared plus z squared. Now that's kind of a special case. To do the rest, I'm going to use a geometric argument. Suppose I want to find the distance between 2 points P and Q, right? Point P, point Q. I want to find the distance between these 2 points, right? What should I do? Actually, let me draw the point slightly differently. Put the point P up here. Put the point Q down here, just a little bit more easier to see my argument if we do that. My question is, what's this distance? Well, what I would argue is that you could say that that distance is simply the length of the vector which connects the points, right? But the length of that vector should also be the same as the distance from the origin to the point which it corresponds. So I can take these P and Q, I can construct, PQ, right? And that PQ vector, we can picture like this, right? And what do? I just move that PQ vector down to the origin, like so, right? Now, I probably shouldn't call it PQ anymore, right? I should probably call this thing V, perhaps, and say that, well, I don't know, this is... Anyway, it's the same vector down here. The point is that this red vector has what is it? I mean, this point right here is what? I mean, that point is Q minus P, right? So what's that distance? Well, the distance, and of course this is what? This is Q1 minus P1, right? Q2 minus P2, Q3 minus P3. I mean, the point is that. And so the distance would be the square root of Q1 minus P1 squared plus Q2 minus P2 squared plus Q3 minus P3 squared, right? So this is just the natural generalization of the 2 point, the distance between 2 points in the plane, right? We just add a third square and sum the squares of the difference between the coordinates, and that's it. But by the way, definition, if we have vector A, which has, let's say, components A1, A2, an, then the length of A is the square root of A1 squared plus A2 squared plus plus an squared. So this is the so-called Euclidean length, or sometimes called the magnitude of the vector A. I tried to give you some justification for that formula in terms of three-dimensional geometry, but there's really nothing special about three-dimensional. I mean, this is the usual. In fact, I mean, the reason I draw these pictures is to provide a motivation for the definition. Honestly, the things I wrote there are really definitions, if you want to be picky. You could define length otherwise, and it would lead to other ideas. Okay? Like it could be that your x, y, z have the meaning of grades in a class or something, and you want the length to be like a weighted average of the assignments. And then you would count the distance in different directions differently, because it wouldn't be a physical distance, it would have some meaning representing a grade or something, right? Then you wouldn't use Euclidean distance in that space, you'd use something else. But for us, we're talking about Euclidean length. Just there it is. Okay? All right. So what's the length of this vector, going back to my example 1? What's the length of this vector? Has length, so our notation, double bar, QP, and it would be the square root of 1 plus 25 plus 100. So square root of 126, whatever that is. I don't much care, but there it is. That's the length of that vector. Right? All right. All right, let's take a slight break from these elementary things. Let's look at a kind of applied example for a second here. Example 2. Find the midpoint for, let's say, 1, 2, 3, and minus 3, 7, 8. What would a midpoint be? Should be the point in the middle, right? Okay. So the way you do this is you just take 1/2 of 1, 2, 3 plus minus 3, 7, 8. That's going to be the midpoint. So the midpoint here would just be, let's see, we got what? Minus 1/2 times minus 2, 9, 11. The midpoint in this case would be minus 1, 9/2, 11/2. There you go. What if you wanted to find the midpoint of 3 points? How would you find the center of 3 points? I guess I could try to visualize that. You want me to? I'm going to regret it. So 1, 2, 3 is where? 1, 2. So 1, 2, 3 in my very rough picture is somewhere here-ish. Okay. Where's minus 3, 7, 8? See, this is horrible. So that's into the board, minus 3 units, 7 over in the y, 8 up in the z. So it's kind of like, it's in the limits of my artistry here-ish. So again, very crude, but the midpoint's here. It makes sense, right? The x value is between minus 3 and 1, right? The y value is between 2 and 7, right? 4.5 is between 2 and 7. The z value is 11/2, which is what? 5.5. That's between 8. Is that between? Oh yeah, that's between 3 and 8, isn't it? So you might wonder where on earth I pulled this formula from. You just add it and divide by 2, right? Admittedly, I haven't really explained why that's reasonable, have I? It's the average of the points, right? Why should that be the midpoint? I mean, it seems to have worked, right? I think it's probably more convincing if we work out the idea in 2 dimensions and look at it carefully there. You could derive it carefully. I could spend 10 minutes, and 3 of you would really enjoy it, and the rest of you would be like, move on. So I'll let you come talk to me about it in office hours if you want to see that. But generically speaking, if you have n points, you can just add them all together and divide by n. That will give you the geometric center of those points. The other place you might see that idea is in physics, where we find center of mass, right? But there, you take the points, also multiply by the masses, and then you divide by the mass. I would say it's a weighted average, but we don't multiply by g. So, sorry, it's a horrible joke. You'll understand it later. Let's see here. Where are we? You're like, you're getting behind. It's like, okay, very good. Yes, that's probably accurate. So it's hard to do much in here before we get to dot products and cross products. All right, dot products are so much of They drive so much of the analysis in here, vector-wise. There are a few things I can do before that. Here's another thing I could do before we get any further. We could find the parameterization of a line between 2 points. You guys talked about parameterized lines in Calc 2, right? What's the parameterization of a line in Calculus 3? What's that look like? So I'll give you a definition. The line with base point P and direction vector V has parameterization R of t equals to P plus TV. All right. Draw you a picture. So the idea here, and I'm drawing a three-dimensional picture, but this definition I just wrote works just as well in 2 dimensions as it does in 20. I mean, it's not really a three-dimensional idea. It's more than that. But if this is the base point right here, P, right, and the line we're talking about is this, then this direction vector V, right, so let's see here. How about t equals 1? What would R of 1 be? If you plug it into the formula, we get what? P plus V, right? So we go out here to the, to the point P, and then we add V, like so, right? If that's V. And this point right here would be R of 1. So at t equals 0, you get the base point, right? And then as t progresses, you go along the line by adding scalar multiples of the direction vector V. This is how we describe a line in 3 dimensions, right? Or 4. Now, supposing we're in 3 dimensions, what are the parametric equations here? So let me look at an example. Suppose line L has parametric equations x equals to 3 minus 2t, y is equal to 7 plus 4t, and z equals to 6. Question: what's the parameterization of this line? Find its base point and direction vector. Find parameterization of L, including base point and direction vector. All right, does that question make sense, given the data? All right, so here's how we do this. For this one, we have R of t equals to what? It's equal to 3 minus 2t, that's the x. The y, 7 plus 4t. The z, 6. And then what you got to do is just sort of unadd them, so to speak. So this, if you look at it, is 3, 7, 6 plus t times minus 2, 4, 0. Now, if you don't make the vector, I'm angle bracketing them to emphasize I'm thinking of it as a vector. You could make them parenthetical. I wouldn't take off points. It's just for geometric emphasis, okay? But anyway, so you can then tilt your head and squint and identify what's the base point. Right, this is the base point. And the direction vector is this guy. Looking ahead a few lectures, it also happens to be the velocity of the line. Pikachu? No. Is that Pikachu? No. No. Okay, good. I was worried. Okay, so parameterized line. Is there a nice formula for the line which goes between 2 points? What if I want to parameterize the line that goes from, say, point P to point Q? How would you do that? Well, I'll just leave that out there. I'm going to come back to that later. I just want to introduce the concept of a parameterized line. That's what it is right there. So, all right, so let's talk about the dot product. What is it? Why do we care? What's it do for us? What it's really about is projections. Right. So here's the definition. If we have vector A and vector B, n vectors, okay, then A dot B is equal to A1 B1 plus A2 B2 plus dot 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 plus AN BN. So a dot product takes two vectors, all right, and it gives you back a number. Okay. So for 2 dimensions, I'll give you some examples. Example 4. So if I had, say, 1, 2 dotted with 3, 4, how would I get? What would I get here? 11. Okay, so I get 1 times 3 plus 2 times 4, which is indeed 11. Thank you. All right. Example 5. What if I have vector ABC, right, and I take the dot product with x hat? How would we do that? Uh-huh. So what he's doing, so you're just thinking about this in your head, right? Yes, this is A times 1 plus B times 0 plus C times 0. And that works out to A, as you said. Yeah. How about ABC dot y hat? Yeah, it's just B, right? I think you know where I'm going with this. How about z hat? What do we got? Right. So what's this mean? This means that we can put all this together. In retrospect, we can write V is, what is it? It's actually V dot x hat, right? Plus V dot y hat, plus V dot z hat. Yes? Maybe you should put in your Batman. Become Batman. Here, be the Batman. There you go. No? All right. Yeah. So the dot product is very significant in the sense that it allows us to select components of vectors, right? Like taking the dot product of the vector with x hat picks off the x component. Taking the dot product with y hat picks off the y component. Taking the dot product with z hat picks off the z component, right? And those are projections, right? That's the length of the shadow of the vector onto that particular coordinate axis, in a sense. I mean, questions? Okay, so what are the properties of the dot product? Right. So we have that A dot B is equal to B dot A. That's kind of nice. It's commutative. You can pull scalars out, right? If I have like A dot a scalar multiple of B, I can pull that constant out, right? What other nice properties does dot product have? It distributes across addition. So if I have like A dot B plus C as vectors, or let's say V and W, A dot V plus W vector, well, that's A dot V plus A dot W, right? So the dot product enjoys really nice properties. I mean, it's part of the reason we call it a product, is it behaves like a usual multiplication. But you got to be careful, right? The dot product is not a vector again, it's a number. Okay? Now, you start to see some of its geometric significance. It tells us something about components here, right? But there's more, right? There's some deeper identities that are known for the dot product. Let's see if I'm missing any. I think that's mainly it for the main algebraic ones. What if we look at A dot A? What's A dot A going to be equal to? It's A1 squared plus A2 squared, right? Plus A3 squared, and so forth, right? What is that? I mean, I think I defined it just over here, right? The length of the vector A is the square root of the sums of the squares of the components. So you see what that is. This is the length of A, right? Squared. So if we already had discussed the dot product, like civilized human beings, the best way to have this discussion is just to define the dot product and go from there, honestly, from a sort of just purely from the viewpoint of logical efficiency. But anyway, we have at least found another way we could have defined length would have been, say, the length of A, right, is the square root of A dot A. That would be entirely equivalent to the formula I gave you about a half hour ago, right? So dot product tells us about the length of a vector. Now there's more. Let's see here. Working myself into a corner because we don't need these things anymore. I'm just kidding. Actually, there will never be a point in this course that you don't need the things I wrote just on this board. These things you must know. Memorize these things. It's important. We do talk about lines on and off for the rest of the course. And do you see why I mean, you have a single vector equation, right? You could eliminate time here, and to write the equation of a line in terms of Cartesian variables, you wouldn't need one equation, you need like two. So to talk about a line in 3 dimensions, you actually need 2 equations in terms of just x, y, and z, right? So that's why the parametric viewpoint's better, because we just talk about the parametrization. We don't have to fuss with multiple equations and looking at common solutions and so forth. I'm getting ahead of the story. We'll come back and talk more about that in a different lecture. But let me get back on track here. So these are some deeper things. About the the vector length and so first of all, if I have, what's the length of a scalar multiple? C times A, what's the length of this? C, now, okay, so almost on board with you there. So why is that wrong, guys? C is a scalar. It doesn't have to be positive, though, right? So what we have to do is we have to put absolute value to be right there. So if we pull a constant out, we pull out the absolute value of the constant. We also have this wonderful result called the triangle inequality. The length of A plus B is less than or equal to the length of A plus the length of b. The reason that's called the triangle inequality is this picture, right? If you can, well, let me just, I don't need to keep drawing coordinate axes like we need to look at coordinates here. This has nothing to do with coordinates. So if this is A, right, and this is B, then where's A plus B? Well, A plus B is this, right? So it stands to reason that the length of A plus B should be smaller than the length of A plus the length of B, right? In fact, when would you expect that they're equal? When there's no angle. All right, so like when A and B line up in the same direction, right? So if A and B are pointing in the same direction, right, then the length of A plus B should be the length of A plus the length of B. But otherwise, it'll probably be smaller. I mean, it will be smaller. This is a homework problem you'll find in certain books, okay? Now, you're like, well, that's a geometric proof. That's true. If you'd like to see an algebraic proof, it's on page 20 of my notes. I derive it specifically from properties of the dot product, right? And just straight algebra. You can derive that. You can also derive, so this is actually 1, 2, I'll give you, this is proposition 1.13. Now, number 3 on that is something that's a little bit trickier to prove, but equally important, so-called Koshi Schwarz inequality. Koshi Schwarz inequality says that A dot B, right, the magnitude of A dot B is less than or equal to the length of A times the length of B. So this is the so-called Koshi Schwarz inequality. Again, there's a proof in the notes if you want to look at it. I don't guess I'll do it in here today. Right. And then, well, 4 and 5 are kind of more obvious things. 4 is that the length of a vector is non-negative, right? You can't have a negative length for a vector. And then 5 is that the only vector with 0 length is the 0 vector itself, okay? But this Koshi Schwarz inequality is important because what it means is that if you look at this quantity, if we look at, A dot B, and we divide that by the norm of A times the norm of B, right? Yeah, you can play. Just make it quiet. He's got this watch with games on it, you know. So this, if I just divide by that, what's this? This says the absolute value is less than what? So if I put this, I got this is less than 1, right? But that implies that A dot B over the length of A times the length of B is between 1 and minus 1, because the dot product could be positive or negative, right? And that means that you can assign an angle. You can pick theta, an element of, say, 0 to pi, such that the cosine of theta is equal to A dot B over the length of A times the length of B. And in fact, you could investigate this more carefully, and you could show that that angle, algebraically defined there, has to match the geometric angle, which you naturally view as going from vector A to vector B, by applying the law of cosines to an appropriate plane which contains the vector A and B, the arguments in my notes. So this gives us the definition. So definition for A and B non-zero, the angle between A and B is equal to is equal to the inverse cosine of A dot B over length of A, length of B. So, I mean, obviously a special and important case there would be when the angle is 90 degrees. What would happen when we had 90-degree angle? So again, I'll write it over here. The angle between non-zero, A and B, is given by inverse cosine of A dot B over the length of A times the length of B. Phew. Are you getting tired of writing double vertical lines for length of A and length of B? I am. I'll stick with it just a little longer. I always use that notation on and off, so it's not like a waste of our time that I'm doing it now. It's just, in this context, I could just write A without a vector and B without a vector for the magnitude as I shared with you last class, if you want to write less. That's the angle. So we say A is perpendicular to B. What's that mean? A perpendicular to B if theta, let's call this thing theta, right? Theta equals to what? 90 degrees, right? Or pi over 2, if you like. We're not doing calculus yet, so it doesn't really matter. So that's going to be true if and only if what? A dot B is what? Right, because the only way we can get cosine, inverse cosine to be 90 is when we've got, I mean, cosine of 90 is 0, right? So, yeah. So this right here, sometimes we'll say that A and B are orthogonal. It's another term which is used a lot. Orthogonal for us is just a synonym for perpendicular, okay? Any questions about this? All right. Logically, there's something I missed in my discussion of projections a few minutes ago. I'll come back and pick that up here a minute or two. I think before we do that, though, I'll give you an example where we actually find some angle here. So suppose we got 3 points in space. What example am I on? Example 4, 5, 6. Yeah, 6. So let's see here. Hiram, pick a point. You know, pick a point. Three-dimensional point. I just need 3 numbers. 1. Mm-hmm. 7. All right. And let's see here. Who else would like to pick a point? Somebody give me a point. 2, 2, 2. All right. Anybody else want to play? Give me another point. 3, 6, 5. Jinx? No. Okay. 3, 6, 5. Okay. So let's picture these sort of schematically. I'll put the point P here. I'll put the point Q out here. I'll put the point R down here. Again, this is just an organizing picture. It's not really, I'm not even thinking about a specific X, Y, Z coordinate system or anything like that. You don't need to. This is just an organizing picture, a mnemonic, if you will. And so I want to find, here's the question, find the angle here. In other words, the question I'm asking is find angle between PQ and PR.